Let's look at cartographic modeling. You should also be reading the TROD Cartographic Modeling PDF that is in the Brightspace module. Cartographic modeling is simply a generic way of expressing and organizing methods by which spatial variables or map layers are used in operations to develop a GIS model output. And it's basically a flowchart of your inputs, the intermediate outputs, so those are called intermediate, and the final output. And there can be many intermediate steps within that type of a context, but it's basically flowcharting. So cartographic modeling is a way of flowcharting that has specific conventions that are used that aren't particular to specific software. So cartographic modeling is something you can do with or without software, although many software, even ArcGIS Pro, contain the ability to develop cartographic models and run them visually, to visually create and then run the model, which is a big advantage. And the cartographic model describes the interactions that happen to layers or between layers to create that output. And modeling is simply the process of making a model, or this special type of flowchart. And it's a process of linking together a set of basic operations called cartographic modeling processes that work on layers into some logical sequence to produce the desired output. And we can do this in Model Builder in ArcGIS. And that process of creating that flowchart, specifying the input layers, and the sequence of operations on those inputs to produce an output is simply called cartographic modeling. And it requires processes or statements. A process is what we do visually in a flowchart. A statement is something we use in what's called map algebra, and we'll see the relationship between cartographic modeling and map algebra very shortly. But for now, cartographic modeling is synonymous with processes. These are single operations on one or more input raster layers. And these generally represent a tool, just like you've used before in ArcGIS Desktop or ArcGIS Pro. You run a tool on something. Well, that can be represented as a flowchart with an input, the tool in the middle, and the output on the other end. So each process has an input layer, a function, which is a tool in our toolbox usually, and an output, which is the name of the derived data set. So a derived data set is a special term, which means the output data set, something that is different from the input because of the function or tool that was applied to it. These processes, once we have more than one of them linked together, then we have a model. And in the context of map algebra, it would be called a program. So we have models and programs, and we'll see map algebra relationship in a second, but with cartographic models, we have a model, and that provides a bunch of linked together processes to produce an output, a full flowchart, so to speak. So here's what I'm talking about visually. We start with a generic process at the top. A generic process is this tuple. This is three things that must always occur together within a cartographic model to represent anything done to a layer. The layer is called the input. What happens to the input is the toolbox function. And then we have an output that has changed the input values in some way based on the function in the middle. And that's just called generic here because it's not specifying a particular input layer or a particular function or anything particular about the output. But that is the basic atomic building block called a process in a cartographic model. We make it specific by giving it specific names to the inputs, the outputs, and the functions. So a specific process model is like this: elevation. So that's an input. And then we run a slope operation on that, a slope function. And that produces an output we call slope out. So it transforms the elevation values into slope of land. So that's called the specific model now. We can have single processes, such as this. For example, DEM, digital elevation model. Surface slope, so we get slope of that and slope out, just like we saw before, just the name of the input is different. Or we can have operations, which would be your mathematical operators represented in this notation. And for example, math times, so multiplication. And here we have 0.3048 times a elevation model in feet to convert it to meters, and the output we call DEM meters, or M for meters. So these are single processes. We can have single, or as single processes, they can be parallel. So here's a parallel process, for example, that uses the same input on two different functions to produce two different outputs. The DEM elevation model goes into a surface function to get aspect, and we have an output aspect. It also goes into slope to show an output called slope out. So the slope and aspect of the land, where the aspect is the direction of the steepest facing slope. So that's another type of single process that's called a parallel process. Processes can also be chained or compounded. And once we do this, we then have a cartographic model. So for example, here we have a single process. And again, this is just showing a generic process idea where we input a function and an output. And then we use the output as the input to the next function. So we have two complete processes here. The first process, input function output, and the second process, input function output, where the input is the output of the previous one. And then here we have a model. Map algebra is related to cartographic modeling. We have processes or statements, and statements are what we have for map algebra. So this is, instead of using flowcharts, representing a sequence of operations in functional notation. Like we see here, we have output equals a function of the input. So output is a function of the input, where f here of input, or we could also just say f at x, is some function or tool in our toolbox. That is contrasted with cartographic models, which represent the same type of statement in a single process. So these are the atomic units of map algebra statements or processes for models. Here we have just an inverse of the map algebra notation, represented as the cartographic model process. So the output is simply flipped. Output is first, equals some function of the input, which now becomes from last here to first over here. So it's very easy to convert between map algebra statements and cartographic models, because each map algebra statement has to have the functional notation that you see here. Output is a function of input. That's one single map algebra statement, and that's equivalent to one single cartographic process. When we have multiple map algebra statements together, then we have programs, which can then be run in Python, for example. Map algebra is really the central component of cartographic modeling with raster, in that the majority of geoprocessing is done using map algebra rather than cartographic modeling. The simple reason being that map algebra is much more efficient and quick to work with compared to cartographic models, because cartographic models get very large very fast and can become visually difficult to see what's going on. Now, map algebra syntax is different among all GIS software, and sometimes even within the same software. So the syntax of map algebra, that is the grammar of the language that's being used to implement map algebra, is different. And so understanding the conceptual level of map algebra, that the output is a function of the input, and putting those together to create programs, is the most important aspect of map algebra. Here's a contrasting way that we can do two things or do one thing in the same way, both in generic process or cartographic modeling. So we start with our generic process for a cartographic model process. We make it specific. We've seen this. Elevation, then we have a specific function and then a specific output name. In map algebra, the generic, or I should say the specific model process, becomes slope is a function of elevation. And then we look for the syntax for map algebra. And this is in the help file for every geoprocessing tool. It tells you how to use it. For example, here, slope is a function. It takes an input raster. So that's that part of the equation right there. And optionally, these two optional parameters. Once this is assigned, the syntax is dependent on the software you're using. We use ArcGIS Pro, and there's a function called slope in the geoprocessing toolbox called spatial analyst. And then we can have an operational function, which is something we would actually type in to the Python window, given that we have a layer called elevation. And we want the output measurement to be the degrees and Z factor to be the default of 1. You can read about what those are, and so you should always look at the help file for slope to see what the meaning of each of these parameters are here. So we then have an operational function, which again is equivalent to the specific model process up there. Two ways of doing the exact same thing. And the way you choose depends on pretty much how many things you have to do. But in all cases, the operational functional form will be much quicker for you to use in geoprocessing than creating models. Let's understand a little bit about the way in which we produce statements in map algebra. So here we have our output equals a function of input equals something. So what are these things in there? Well, input, so you notice it says function of input equals, that input is called a function parameter. And what we set that parameter to is the argument. So a raster is an actual raster that exists in your table of contents, for example, and input is what the function you're using calls that particular required parameter, and it defines the input as having to be a certain type of thing. So we have parameters and arguments. Here, and if we look at the slope function itself, the syntax, slope in underscore raster, comma, and then in squiggly braces, output measurement, squiggly brace, and squiggly brace Z factor, squiggly brace. That's the braces here I'm talking about there. The ones that we call them squiggly braces. So if we look at our output, our general statement up top, output equals a function of input equals something, well, that input in a particular function will have a parameter name like that in raster. The parameter argument will be something that you have existing as a layer, either in your table of contents or within your folders that are attached, or your geodatabase, default geodatabase, for example, in ArcGIS Pro. So for example here, elevation. Elevation then is the equivalent of this thing here saying a raster. So input equals a raster. So we would say in raster equals elevation, like that, to complete the syntactical statement that can then be run and operationalized within the Python window in ArcGIS Pro. We can also have non-named parameter arguments. So ArcGIS knows that the parameter in raster will be replaced by elevation in this syntactical form. Since elevation is the first thing we put in here, it automatically assigns it to in raster. So we don't have to type in raster equals elevation. We can just say slope elevation, and because it's the first thing, it assigns the first argument to the first parameter in raster automatically. And that saves a lot of typing, and most of the time you'll just see statements like this in map algebra. you don't see the explicit typing of the parameter name. So here's the final in map algebra. Just we have single processes. So we have DEM, slope, slope out, and again, these are both at a slight level, different level of abstraction, but they can be equivalently said in map algebra. Slope out equals slope DEM. So using that slope function. So these are two things that can be operationalized. To multiply a raster by a constant value, let's say to turn feet into meters, we would have to say this type of single process in cartographic modeling. 0.3048 would be an input to times, and DEM in feet would be the other input. Times equals DEM in meters. And clearly that is a much larger construct visually and in terms of time than simply saying DEM underscore meters is the output is equal to some number times an input layer called DEM, or raster variable called DEM. And we'll see many examples of these